This next problem is a little more complicated than the ones that we've looked at up to this point. But it is reminiscent of what you did in lab when you were looking at the specific heat of the metal cylinder that you were provided with, and you looked at the interaction of it with the water in your styrofoam calorimeter. In this problem, we're going to take an iron sphere that we've heated up to the boiling point of water. We're going to transfer it over to a styrofoam calorimeter that contains water that's a little bit below room temperature, and we're going to see if we can find the final temperature of both the iron and the water. Now remember, this is actually fairly simple if we keep in mind just one fundamental idea here. The iron is going to give up heat, the water is going to gain heat. We will record our final temperature whenever there is a thermal equilibrium reached. The water and the iron sphere will be at the same temperature. If you keep this in mind, it gets you started by writing an equation that illustrates that situation. And here's our equation. We're stating mathematically what we should be reasoning through on our own, and that is that the heat released by the iron should be equivalent to the heat gained by the water. Notice the actual quantities will be equal, but we have to put the negative sign in there because one is releasing heat and one is gaining heat. There's no way they could be equal without adjusting the sign. It really doesn't matter which side you put the negative on. In this problem, I don't know what the heats are, so I'm going to substitute in with an expression that is equivalent to the heat, realizing that neither the water nor the iron are going to undergo a phase change. We can substitute in using our relationship Q equals mc delta T. I've substituted on the left side for all values involving iron, and on the right side of the equation, all values that pertain to the water. I go back into my text of the problem and I ferret out the mass of the iron, 88.6. I look up its specific heat. I don't know what the final temperature is. That will be my variable. On the right side, everything pertains to water. The mass, 175 grams. The specific heat, obviously, is 1.0. Again, at thermal equilibrium, T2 will be the same for the water, so I can say I'm only going to have a single variable that I have to solve for. This is a fairly simple algebraic equation to solve for T2. I go ahead and distribute across my binomial on the left side with the iron, and then again on the right side with the water. We'll use some algebraic principles, consolidate the constants terms, and then consolidate the variable terms. I'm using a little arrow to indicate where the significant figure is in the 4000, for example, so that I don't put this in scientific notation. I just find it easier to do it that way. Then all we have to do is divide through each side by 185 and solve for T2. And I'm anticipating getting a value that is between 17.4 and 100.0, and sure enough, I end up with a value of 21.6 degrees. So this is a check for yourself. You have to get a number that is not lower than the cooler material and is not higher than the warmer material.